We looked at Lewis structures because that's important to work out shapes, and we had to know shapes because we were looking at, or to work out polarity of molecules, and that's what we did last week. Now we know polarity, whether a molecule, we can work out whether a molecule is polar or non-polar. We can then work out what sort of attractions are going to be between those molecules. So those are our intermolecular forces. Inter, between, molecular, molecules and forces. Normally we just talk about the molecules, the covalently bonded non-metal discrete groups like CO2, H2O and so on. We normally don't talk about intermolecular forces between things like sodium chloride because that's ionic. But if you look at the internet, you'll see sometimes people, especially Americans, tend to use intermolecular forces for all sorts of things. Okay, but New Zealand, I'm just pointing out, it's between molecules. So if you have a molecular solid that you learned about, say, at level 2, this is the forces of attraction between the molecules. Now, if I say intermolecular forces, what do you think of? I'm just trying to think of your level 2 understanding. So, is anybody brave enough to type something down? Okay, Nicholas, great. So, because this is the step up, okay, the forces of attraction between molecules, yep. And some people will say van der Waals, or they'll just say intermolecular forces. So this is the step up between level 2 and level 3. And you can't achieve this part at level 3 if you don't show that you know more than at level 2. So at level 2, you just simply said there were weak forces of attraction between the molecules, and that was it. So it's a low boiling point. Level 3, you have to identify, and we look at 3 different types at level 3. There are more different types, but these are the ones we look at. So the first type is called, now hopefully you can see this, temporary dipole, forces of attraction. Okay, so this is the temporary dipole. Also, it's got other names. Instantaneous dipole. Instantaneous, it's there for an instant, then it's gone. Okay. Also called London forces, particularly in the States. If you watch YouTube clips from there, it's after a chemist called London, not the place called London. Or dispersion forces. And it's part of the van der Waals group. So van der Waals has a whole lot of different types of intermolecular forces in it, and the temporary dipole being one of them. Now you'll get this in all molecules. So you'll get it between water molecules, you'll get it between butane molecules, you'll get it between oxygen molecules, you'll get it between hydrogen sulfide, or so on. So it doesn't matter if the molecule is polar or non-polar, you're going to get these forces of attraction, because what causes these forces of attraction is simply the electrons as they're moving around the molecule. Sometimes they're not moving all evenly like in a well-aligned traffic moving around. Think of it as being a very random traffic movement. You know, sometimes you have lots of cars and you have to go slowly, and then you have no cars and you can go fast, and so on. So electrons are the same. So sometimes you'll have the electrons bunched up on one side of the molecule just for an instant, and then they separate out and they get more evenly dispersed, and then they're bunched up on another side. So when they're bunched up on one side, that side of the molecule becomes more negative because there's more of them there, and the other side would be more positive because there's fewer of them there. So this is what we mean by these temporary dipoles. They, in an instant, as the electrons move around, this side becomes a bit more negative, a second later that side becomes a bit more negative, and so on. So would you expect these forces to be strong or weak? Weak. Okay, they are generally the weakest. I'm going to say generally because there are certain factors that affect them. One of them, remember I said if the electrons all bunch up on one side, so can you imagine the more electrons I have, the more it could bunch up, and so the more negative it could be. Okay, so you get that idea? So the size and the mass of the molecule is important. So when you explain this, so this is for your merit and excellence, you have to explain these factors. The mass of the molecule. And you can do that even at isotope level. They can be actually even at the same number of electrons, but if the nucleus is heavier, so like deuterium compared to hydrogen, there is a different attraction. In fact, this is how they make heavy water. It's based on the difference in attraction between D2O and H2O. So if I have got two molecules that are identical in terms of mass, okay, they will have a stronger attraction between them if I have some other molecules that have a heavier mass. So the heavier it is, the stronger those attractions will be. Normally it's the same thing, unless it's an isotopic thing, but normally the heavier the molecule, the more electrons. And again, the more electrons, the more they can bunch up, so it's going to be a stronger attraction. And the shape of the molecule is important. So there's three things you have to talk about when you're explaining this. And so you'd be talking about, if you're comparing the boiling point of water and oxygen, you would be talking about the mass of water compared to the mass of oxygen. Water is lighter than oxygen, because water is 18, oxygen is 32. So oxygen will have bigger temporary dipole forces of attraction than water. Okay, so but water still has these forces of attraction. So here for the shape, I'm trying to show a round molecule. So there's not much point of contact, so it can't form very many attractions between them. But if I have a more longer molecule rather than round, I can have more points of contact between them. Okay. Now, Nicholas, you said, are these forces noble gases? Yes. So the noble gases, this is what causes noble gases to form liquids under a low enough temperature and so on. And that's why, for instance, helium has got the lowest boiling point, because it's got the weakest temporary dipole force of attraction, because it's the lightest. Xenon, although it's a gas, it's got stronger temporary dipole forces of attraction because it's a heavier molecule, more electrons. The shape's the same, they're pretty much round. Okay, right, so they can, as I say, they're normally weak, but please don't get it stuck in your mind that weak molecules, that these are the weakest and will always be weaker than anything else. Okay, we will look at examples where you've got only these force of attraction, but it's a liquid or a solid because of the mass and the shape and so on. Okay, permanent dipole force of attraction. This is when, remember we're talking about polarity of molecules. If you have a polar molecule, you've got permanently on one side of the molecule a negative end and permanently on the other side of the molecule a positive end. So they're always there. So they're not there in a split instant and then they're gone again. So these tend to be stronger forces of attraction. What do you think will influence the size of the attraction for the permanent one? If it depends on the permanent dipole, what is going to influence it? Well, the shape is going to determine whether it's polar or non-polar. So Abigail, in a way you're correct, but it's not shaped like as in the temporary dipole, where a linear molecule has stronger temporary dipole forces of attraction, because you can form more of them compared to, say, a round shape. But yep, Caleb, yes, the molecular dipole strength. So for instance, if I have H2O and H2S, now they're both bent molecules, but oxygen, is it more electronegative? So Nicholas, you also write in a roundabout way. Oxygen Is it more electronegative or less electronegative than sulfur? More. So if it's more electronegative, what can you tell me about the molecular dipole in H2O compared to H2S? It'll be bigger, and therefore if the molecular dipole is bigger, you're going to have a stronger permanent force of attraction. So you will need to know your periodic trends. So if you get given something like H2S and H2O, you can say that the H2O will have stronger permanent dipole forces of attraction. Okay, and the stronger any of these attractions are, the harder it is to separate the molecules, so the higher the boiling point. Okay, you only found these in polar molecules, not non-polar, so you must be able to identify whether a molecule is polar or non-polar. Okay, and as I say, it's only influenced by the molecular dipole, not the number of electrons that affects the temporary. So what I've got here is if I don't have much of a molecular dipole, it's a weaker attraction. If I have a much bigger separation, a bigger permanent dipole, or bigger molecular dipole, I'm going to have a stronger attraction between them. Do you think you are okay, you're clear between those two? Right. Okay. So what I want to show quickly before I go on to the next one, I'm going to get out of here. This is a thing that is by ChemSite. I'll put this, when I upload the video, I'll put this on here. But it shows you very nicely the difference between the temporary and the permanent dipole forces of attraction. So what we've got here at the top, and I'm going to make it perhaps a bit bigger, so hopefully you can see a bit more. Let's try one more. Okay. If I go average over time, can you see these are non-polar molecules? Okay. The electrons are, on average, evenly distributed over the molecule. This is a polar, these are polar molecules because you've got one end that's positive and one end that's negative. But as I say, these electrons, it's like a constant traffic moving around. So you get traffic jams and then you free flow and so on. So what we're trying to show here is as electrons move around, they can bunch up. And of course, if you've got one end that's slightly negative, it's going to affect the one that's next to it and make it slightly positive because it's going to repel the electrons to the other side. So you've got these electrons whizzing around all over the place, each molecule influencing the other one. And so they all these instantaneous attractions. They're there and then they're gone. With the with a polar molecule, can you see I've got these permanent attractions? Okay, so if this is in a solid, they're going to line up negative next to the positive and so on. So I've got these permanent dipole forces of attraction. But can you see it's also flickering away? Okay, it's not, if I go back to average, that's not flicking, okay? So that's always at a particular positive and that's always at a particular negative. But in the instantaneous view, you can see it sometimes gets a bit more positive and a bit less positive and a bit more negative and a bit less negative. So that's the influence of the temporary dipole forces of attraction. And as I say, the more electrons you have and the heavier molecule, particularly if your permanent dipole isn't very big in the first place, then these attractive forces can outweigh the strength of the permanent dipole force of attraction. So I think this visualizes very nicely how, because a lot of students forget about the temporary dipole force of attraction in polar molecules. They are still there, and the more electrons there are, and the heavier it is, the more the effect will be. Okay, so does that hopefully make things clearer? Okay, then the last one is, sorry, hang on. I meant to go to the next, I forgot about this bit. So this is the bit about usually stronger than temporary dipole force of attraction. These are the permanent ones. But as I say, your mass can influence things. So like take, for instance, carbon tetrachloride. Hopefully you'll know it is non-polar because it's a tetrahedral shape which is symmetrical as well as only chlorines around the central atom. So the type of atom is the same, so this molecule is totally symmetrical. Look at its boiling point. Okay, 76 degrees. It's a liquid at room temperature. If I have chloromethane, okay, that's a polar molecule, because although it's tetrahedral, the types of the atoms around the central atom is not the same, so the molecule is asymmetrical. So it's going to have your permanent dipole forces of attraction. But can you see it's a gas at room temperature? So we've got something that's a non-polar compared to something that's polar, but this one has got stronger forces of attraction than the polar one. And that's because of the temporary dipole forces of attraction being dependent on mass, and the mass of this is way, way, way bigger, nearly 4 times bigger than the mass of this. Does that make things clear? Yeah. Okay. So here's another one, but we have gone the other way. This is a non-polar, but it's light. Okay, it's only 12 plus 4, 16. This one's a little bit heavier, and it's polar. So you can see there's a big jump up. It's still minus 78, but it's still a lot higher in boiling point than that one. Notice that although fluorine is very electronegative, notice it's got a lower boiling point than chloromethane, and that's again the difference in mass. So chloromethane is heavier, got more electrons than fluoromethane, so it's got a higher boiling point because the attractions are stronger. So you need to think it through. You can't just say it's got stronger forces of attraction. That is level 2 thinking, you get 0 for it. Okay, so hydrogen bonding is like the extreme end of permanent dipole force of attraction, and we give it its own category really. You only find it in N, O, and F. A common question is, why isn't chlorine there? Because if I look up at the tables, chlorine and oxygen have the same, or chlorine and nitrogen have the same electronegativity. It's because the nitrogen is smaller than the chlorine. So the hydrogen is closer to the nitrogen, so nitrogen can suck up its electrons much more strongly and leave hydrogen more exposed. With chlorine, chlorine might have the same electronegativity, but because it's bigger, the hydrogen can't get as close to the chlorine, so those bonding electrons aren't as close to the chlorine nucleus. That attraction is actually not as strong. Okay, right, so you'll only find it, and this is a common error when people are trying to describe hydrogen bonding. Always read over your definition when you write it, because ask yourself, is it clear to the teacher that the teacher can see I'm talking about one molecule and another molecule? So in other words, the hydrogen of one molecule with the oxygen of another molecule. Because when you're trying to explain hydrogen bonding, you first of all got to explain that a hydrogen must be covalently bonded to an oxygen to get that naked hydrogen effect. Okay, so that's like your naked hydrogen. And then the actual hydrogen bond is between the hydrogen of one molecule with the oxygen of another molecule. A lot of students, when they write the definition, it's not clear. It sounds as though you're talking, it's all in the same molecule, and we don't know if we're talking about a covalent bond or an intermolecular force. So just read it over and go, is this clear what I'm talking about? Okay, so that's why the hydrogen bond forms between this hydrogen of one molecule and the oxygen of another molecule. Try and stress that another molecule is involved. But we, of course, only get it if within a molecule the hydrogen is bonded to an N, O, or F. So I can't have, for instance, methane, CH4, hydrogen bond to water, because in CH4 there's no hydrogen bonded to an oxygen in methane. So that first point isn't fulfilled, so I can't have the second point. Is that clear? So you all get this idea of when hydrogen bonding is possible and what hydrogen bonding is. So always have Always explain both those points. Show your examiner you understood those 2 points. Okay, and it's normally the strongest. Very, very, very big molecules, the temporary dipole force of attraction can trump it. I mean, that's why, for instance, wax is a solid, because those non-polar molecules are so long and big. But otherwise, you'll find, for instance, water has got a much higher boiling point than a lot of other substances. Okay. Then also with solubility, there's 2 aspects when you look at hydrogen bonding. Looking at hydrogen bonding within the substance, and then looking at hydrogen bonding with water. Because can you see that if I have a substance that contains oxygen, take for instance, none of you have done organic chemistry. Well, have I got? Okay, yes. Okay, here's a formaldehyde. You'll get to this when you've done organic chemistry. Can you see that I don't have a hydrogen attached to this oxygen? I have a hydrogen attached to carbon, but they can't hydrogen bond. Okay, because they're not bonded to the oxygen. But can you see water? Its hydrogen can hydrogen bond to the oxygen. So formaldehyde, or methanol if you want the IUPAC name, is soluble in water because it can, or water can form hydrogen bonds with it. However, formaldehyde is a gas because it can't hydrogen bond within itself. So its boiling point is low because it can't form hydrogen bonds. It's only got temporary and permanent dipole force of attraction. But it can dissolve in water because water can hydrogen bond with it. So that's why I say you must think of these 2 distinct separate points when you talk about it. Okay, so very quickly, because we've got about 5 minutes left. Here, let's see what our intermolecular forces are. And I've drawn the sort of the Lewis structures to give you an idea, but of course remember this is not planar. I hope you can all see this will be tetrahedral. What sort of intermolecular forces will I find in BRF3? Or to make this quicker to type, just say, am I going to have 1 type of intermolecular force, 2 types of intermolecular forces, or 3 types of intermolecular forces? So how many types of intermolecular? 2, correct. It'll be both temporary dipole and permanent dipole. Temporary because it's a molecule and all molecules have it. Permanent because it is a polar molecule. So we'll have permanent dipole force of attraction. What about methane? 1, 2, or 3? 1. Because it's non-polar, so it only has temporary. It won't have permanent or hydrogen bonding. What about ozone? 2. Because it's polar, okay, the ends are actually a bit more negative than the middle bit because it's actually got more electrons around it. So it'll have the temporary and the permanent dipole force of attraction. What about methanol? 3. It'll have the temporary because it's a molecule. It'll have the permanent because it is a polar molecule. And it will have the hydrogen bonding because it's got a hydrogen that is attached to an electronegative oxygen or nitrogen or fluorine, but here it will be the oxygen. Okay, so these are the different types it gets. So the students often just focus on like permanent here, temporary there, hydrogen bonding there. Remember, it does have all 3. And if it's a very big molecule, the temporary dipole force of attraction can be quite strong. Okay, so boiling point. Obviously, the stronger the intermolecular force of attraction, the harder it is to separate those molecules. It's important when you talk about boiling point that you are actually trying to separate the molecules, because that is the difference between a liquid and a gas. In a liquid, all the molecules are close together, all having the attractions. In a gas, they're all totally separated from each other. and they only, as they're zooming past each other, might form a little bit of an attraction, and then they've zoomed past because they're moving so fast. So we want to break all the intermolecular forces to separate the molecules. So you may, for an achieved level, get a question of what is boiling point. A lot of students leave out the fact that it is a temperature. So it is a temperature which you measure in degrees Celsius or Fahrenheit or Kelvin, depending on what scale you use, but it's a temperature with its own scale. Okay, so it's not just, it's the point at which a substance changes from liquid to gas. You get nothing for that. Okay, it's a temperature at which this happens. And as I say, you've got to pretty much break nearly all the intermolecular forces. So a common question in the exam is you get given boiling points or the delta H VAP, which I'll talk about in the next lesson, because that's in the 3043 booklet. You have to explain the difference between them. So the first thing you do is you work out, are they polar or are they non-polar? The second thing you do is you work out what type of intermolecular forces are present. And then the third thing you do is you look at the factors that affect each type of intermolecular force. So this is where I've got to pretty much, okay, I've left out the first bit, is it polar or non-polar? Because you need that to work out if it's temporary or permanent. So this is non-polar, that's non-polar, that one's polar. None of these can do hydrogen bonding, so you would just talk about the temporary and the permanent dipole force of attraction, and you would then talk about the difference in mass, and you can't really talk about the difference in shape because they're all tetrahedral, all round molecules. So it'll be really the mass and the electrons that you would talk about. You could talk about, oh no, you can't even compare in terms of the molecular dipole because you've only got one polar molecule. So I have got here an example of how you would, yes, you could state that the shape is the same, Abigail, right. So here's an exemplar answer. Okay, so you're saying that they're non-polar, so you're stating that they have temporary dipole. I'm pointing out that although this is polar, it still has temporary dipole force of attraction as well as the permanent dipole. And then I'm going into the factors. So the molar masses, you know, you are given a periodic table, so you can always work out molar mass, remember? So you can talk about this increase in size, so it's heavier, more electrons, so stronger forces, temporary forces of attraction, and so more energy to separate the molecules. Abigail, no, normally there is another part of the question where you have to work out whether a molecule is polar or not, where you show that knowledge. They try not to make, although I have seen it once, I think, where everything, all the steps were combined in one. It's just if you go wrong in the first place, then it means the rest of the question is going to be wrong. So if you state something is polar when it's actually non-polar, then there's going to be issues. So they try and break it up. There's often a question about shape. Then there's often a question where they give you the Lewis structure and they ask you if it's polar or not, just in case you muck up the Lewis structure, so they give it to you. And then there's a question about boiling point or solubility. Okay, and then you talk about this polar molecule having the stronger permanent dipole force of attraction, and also that its temporary dipole forces of attraction are also stronger because it's heavier, but it's weaker than that of CF4 because it's lighter. Okay, so we'll stop there.